Welcome everyone. This is the second lecture of chapter 32 on inductance. In this lecture we're going to look at an RL circuit. It's going to have a lot of similarities to the RC circuits, the resistor capacitor circuits that we looked at in previous chapters. The RL circuits stand for resistor inductor, right? And that's what we can see as shown here. So again, the setup is very similar to what we've seen before. But the inductor is doing something a little bit different. Remember, when the current is changing in the circuit, which there, as in the magnetic flux is changing through the loop of the circuit. If the current's changing, then you're going to have some impedance, some I don't want to say resistance, but some EMF that is induced in the opposite direction of the battery's EMF to kind of slow down that change in current. Okay, so let's take a look at what we have in the pictures. On the left side here, you can see a typical RL circuit. It's set up to be able to either be connected to the battery or just connected between the inductor and the resistor, right? So you notice if we close switch 1, which is right here, we're going to get this top loop. The middle picture here shows you what that top loop would look like, right, without the extra wires. So you have an EMF source that's creating a current in the loop. The current then goes into an inductor. When the current is changing, this inductor is going to create an EMF in the opposite direction, right? It's going to be to the right. When the current is constant, which essentially means it has reached a steady state after a little bit of time, then this essentially just acts like a wire. Okay, we're also putting a resistor in the circuit to again represent that in almost all circuits you're going to have a resistor, but also just to make sure that energy is being dissipated throughout the circuit. Okay, the right picture then shows you, well, what if I keep switch 1 open and I close switch 2? And then we have this situation where it's only an inductor and a resistor. It's almost like the discharging situation that we saw with the capacitor. Okay, we're going to talk about this in future lectures, but with these inductors, there is going to be energy stored in the inductor because it is creating a magnetic field that would store energy, right? So we'll look at that in the future. But let's first start analyzing these circuits, right? What does this analysis look like? Well, again, if I think back to what we did with the RC circuits, we used Kirchhoff's rules to write out an equation, right? Specifically, we're going to use a loop rule here. And for this lecture, we're going to focus on the case where you have an EMF source, a resistor, and an inductor. All right, so let's go ahead and write out this rule. We know that the sum of the EMF sources need to equal to 0, or delta V is equal to 0. We're going to go ahead and start here by the EMF source. So I'm just going to use this dot right here on our circuit to start with. First thing we go through is the EMF source, so that's going to be positive because we're going in the direction of the EMF if I kind of go around the loop like this. The second element we get to is the inductor. In the previous lecture, we talked about the EMF that is produced in that inductor, right, what the equation for that was, and that is going to be minus L times the rate of change of current. Again, that I is the current there, don't mistake it for the flux. And then we get through the resistor, which is our last element, so that's just going to be minus IR. And like we said, all of that is going to be equal to 0. Okay, so if you look closely, the form of this equation is pretty much exactly like the form of the equation that we saw with the RC circuit, right? It has the same form, so we could just jump straight to the solution. The solution would look very similar to what we had before. So the current, right, in the RC case we were looking at the equation for the charge, but in this case we're looking at the equation for the current. It's going to be equal to epsilon over R, 1 minus e to the negative RT over L. Okay, and like I said, this has the same form. So you'll notice a couple slight differences. The one thing I'm looking at here is what's happening up by the time constant, right? We know with the RC circuit, it was negative t divided by the time constant, right? Like negative t divided by tau. Well, it's the same thing here, but the time constant is going to reflect an inductor, not a capacitor. So if the time constant, tau L, we're using the subscript L to indicate it's the time constant of an inductor, is going to be equal to L over R, which is the inductance divided by the resistance. So another way of writing this would be I of t is equal to epsilon over R, 1 minus e to the negative t over the time constant, the inductance time constant. Okay. So we're going to take a look at what this graph actually looks like, but before that, let's go ahead and actually work through that derivation, right? It's going to be good to kind of get more practice with that, and I don't want to just kind of skip all of the work that happened in between here. Again, you could just go back to that derivation that we did with the RC circuit and just follow the steps, just using the different variables, right? We're using the L for the inductance instead of the capacitance. But I do want to go through the derivation anyways. So I'm going to go ahead and skip past this graph. We'll come back to what that looks like here in a second. And let's work through that derivation. So we're going to start with the equation itself. Right, epsilon minus L times the rate of change of current minus IR. Now, this is a differential equation, right? You see that we have two different variables. We have t and we have I. They're related to each other, but through this derivative, you also have I by itself. So this is something that's going to take a little bit of work to kind of get to. Ultimately, with all of the differential equations in this course, you're going to at least be able to separate them so that you don't have to really use any other methods. So they should be separable in differential equations. Let's go ahead and do that. So I'm going to put the di dt on one side, and I'm going to put everything else on the other. And I'm going to divide through by L, so it puts an L on the other side. This gets us a common denominator on the right side when I divide through by L. And you can see that this is going to end up being epsilon minus Ri divided by L. Okay. Now, to solve this differential equation, I ultimately want to get the i's on one side and the dt on the other side. So I'm going to take this term and divide it to the other side, and I'm going to take the dt and multiply it to the other side. So basically just switching those terms around. What I end up with is di over Ri minus epsilon is equal to negative dt divided by L. Okay, so again, just to get it of the form that I want it, I want to get I by itself down here. It's going to make our integral a lot easier. So what I'm going to do is multiply both sides by basically multiply through by R. Okay, so if I multiply through by R in the denominator, I get a 1 over R, right? So 1 over, oops, let me show that again. 1 over R is, of course, multiplying it by R. So you're kind of pulling out this 1 over R, or multiplying it through, rather, and you end up getting di divided by I minus epsilon over R, because we multiplied through the bottom by 1 over R. And the right side is going to be minus R over L dt, because we multiply through by R. Okay, this puts us in just a little better of a form here. Now we can take the integral of both sides. So, do the integral from 0 to I on the left side of di over I minus epsilon over R. Just keeping in mind, right, epsilon over R is a constant. The variable here is I. And since we're taking the integral of both sides, this is going to be the negative integral from 0 to t of R over L, which again is a constant, dt. So let's go ahead and look at the result of this. The left side, you can look at a table of integrals and just, find the one that is of this form. But ultimately, this is similar to 1 over x. The integral of 1 over x is the natural log of x. So this simplifies to the natural log of top minus bottom, which of course is just going to be I minus epsilon over r divided by minus epsilon over r. Because ultimately you get the natural log of something minus the natural log of something, which is equal to the natural log of the first divided by the second. So we're using that identity here. And the right side is just going to be minus r over lt, right? Because really you were just taking the integral of dt from 0 to t, which is just t. Okay. Ultimately, we're trying to solve for the current here, so we want to get the current by itself. To get the current out of that natural log, we're going to take the exponential of both sides. So we're just going to do an e to the all of this, and then e to all of this. That, of course, cancels the natural log from the left side, and then we have e to the negative r over lt on the right side. All right, so that's going to be I minus epsilon over r divided by negative epsilon over r is equal to e to the negative r over l times t. Okay. Now we can get I by itself simply by multiplying this to the other side and then adding this to the other side, right? You can do that in succession. So that's going to simplify to the current is equal to minus epsilon over r, e to the negative r over l times t, plus epsilon over r. Right, that last term was just adding that epsilon over r to the other side. And of course, this simplifies a little bit. So our final equation for the current is going to be epsilon over r, 1 minus e to the negative t divided by tau L, where tau L is equal to L over R. Okay. Now, you can also, jumping back to our previous page where we looked at, what if it was just the inductor and the resistor, you could do the exact same thing we did with the RC circuit. You could look at the result, and you would end up with, just throw, it's not really discharging, but the idea of, we'll just call it a discharge. You're going to end up with the same thing, right? But your Kirchhoff's law to get this equation is simply going to be IR plus L di dt is equal to 0, because you don't have that EMF source in the circuit anymore, right? For that switch being closed, the EMF source is cut out. So you're going to start with that, and then of course your result again is going to look very similar to what we got with the RC circuit. It's going to be epsilon over r e to the negative t divided by tau L. Okay, I'm not going to go through that whole derivation. Again, you can just reference back to your RC circuit, and it's pretty much the same thing. Okay, so let's take a look at, what do the results look like? What do these graphs look like? So we know that, the current, and this is for the charging, or for when you have just closed the switch situation, you're starting at 0 current. You're not just instantly going up to epsilon over r. You're going to eventually work your way there. So you're going to sort of asymptotically approach that part. And remember, the time constant, what does it represent? Well, it represents 0.63 of the total current. So it's the amount of time it takes, the time constant represents the amount of time it takes to get to 0.63 of epsilon over r. Right? And then it's going to be 2 time constants, 3 time constants, so on and so forth. But you can see that we start with an increasing current, right? It starts off pretty steep, so you have the most change in flux here at the beginning, or the most change in current, and then it's going to slowly start to decrease where the change in current almost becomes zero, and you've reached your maximum amount of current. The voltage across the inductor works in a very similar way. So because the impedance or the induced EMF is so great at the beginning because the change in current is so great, you're going to get most of the voltage drop starting across the inductor, and then that's going to slowly wane off to zero when all of the voltage drop ends up being across the resistor. All right, so again, on the inductor, it's going to take all the voltage drop at the very beginning, and then as the current starts to reach steady state, you're going to slowly go to zero. And all the voltage drop will be across the inductor, which means all the voltage drop will then be across the resistor, which means the inductor is basically acting like a wire. Right? There's no voltage drop across it, so it's really just acting like a wire. Okay, that's it for this lecture. We'll see you next time.